Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of elementary number theory. In last lecture we discussed about question number 4. In that question we have to prove that the cube of any integer is the difference of two squares. Obviously this is a cube of an integer, so it should be the difference of two squares, and these two squares also should be integers. So in last lecture I forgot that how these two quantities are integers. There is a very simple logic here that you can write in the last of the question. Here n into n plus 1 and n into n minus 1 both are even integers. Both are even integers. How these they are two integers? How these are even integers? Because product of two consecutive integers is always an even integer. We know that the product of two consecutive integers is always an even integer. So you can write these two are also consecutive integers. N into n plus 1. These are product of this is the product of two consecutive integer, and these are also two consecutive integers. So their product obviously is an even integer that is consequently divided by 2, and in result we have this is the inside this bracket is a integers. Now in total lecture we will discuss question number 5. In question number 5a, the statement is find the values of n less than or equal to 7 for which n factorial plus 1 is a perfect square. It is unknown whether n factorial plus 1 is a square for any n greater than 7. This is a very simple and easy question. To solve this question, we just plug in the different values of n which are less than or equal to 7 in this formula, and we check which value of n gives a perfect square. Make a table here and take values of n from 1 to 7, 5, 6, 7, and this is your formula n factorial plus 1. When you put n is equal to 1 in this formula, we have 1 factorial plus 1, that is simply equal to 2. When you put here 2, this becomes 2 factorial plus 1, this is equal to 3. When you put here 3, 3 factorial plus 1, this is 7. When you put 4, this becomes 4 factorial plus 1. 4 factorial is 24, 24 plus 1, this is a 25, and 25 is the square of 5. Square of 5. So this is the first value for which this formula give a perfect square. Next we put n is equal to 5. This becomes 5 factorial plus 1. 5 factorial is 120. 120 plus 1, this is 121. That can be written as 11 square. This is the second value for which this formula gives a perfect square. 6 factorial plus 1, 6 factorial is 720. 720 plus 1, this is 721, which is not a square of any integer. Lastly, this is 7 factorial plus 1. 7 factorial is 5040. 5040 plus 1, this is 5041. And 5041 is lastly square of 71. Square of 71. So the required values for which required values of n for which n factorial plus 1 is a perfect square are n is equal to 4, 5 and 7. For larger values of n, I do not prefer this technique. For example, if you have to find uh, forward values of n factorial plus 1 is a perfect square when your n is less than or equal to 100. But this becomes a very tedious because you know n factorial is an increasing function. When you put a larger value, your answer will be a larger. So that's why in your textbook it is mentioned that it is unknown whether n factorial plus 1 is a square for any integer. So next we move towards question number 5b. Okay. Uh, Next we discuss question number 5b. This is a just true or false question. In question we have positive integers m and n, and we check whether these formula are correct or not. These two formulas are not correct in general. For example, if we take m is equal to 3, n is equal to 2, these are two positive integers. We put these two values of m and n here, this becomes mn factorial, this is 3 into 2, that is 6 factorial, and 6 factorial is 720. If we put these two values on the right side, that is m factorial into n factorial, this becomes 3 factorial into 2 factorial. 3 factorial is 6 and 2 factorial is 2, this is 12. So this shows that mn whole factorial is not equal to m factorial into n factorial. Similarly, if you put these values of m and n in the second formula, that is m plus n factorial, m plus n whole factorial, this becomes 3 plus 2 factorial, which is equal to 5 factorial, that is 120. Whereas if you put these two values on the right side, this becomes 3 factorial plus 2 factorial. 3 factorial is 6 and 2 factorial is 2, that is 8. Again, m plus n factorial is not equal to m factorial plus n factorial. So these two formulas are not correct. Next we discuss question number 6. Okay, next we discuss question number 6. Question number 6 has two parts, and this question is related to mathematical induction. In the first part, we will prove that for every integer n greater than or equal to 4, this inequality n factorial is greater than n cube, n factorial is greater than square hold. And when your n is greater than or equal to 6, then n factorial is greater than n cube. I will solve the first part, that is n factorial is greater than n square, and I hope you can solve the second part by yourself by using the same steps that I will discuss here. Suppose that this statement is denoted by P of n. Let Pn be the given statement, Pn be the given statement, that is Pn is such that n factorial is greater than n square for all n greater than or equal to 4. This is our requirement that we have to show. I am using here Principle of Mathematical Induction that says base step. Firstly, we check the statement, is the statement true for n is equal to 4, because here our starting values of integer is 4. So firstly we check the statement for n is equal to 4. When you put here n is equal to 4, this becomes 4 factorial greater than 4 square. The left side is 24 and the right side is 16. That is true. So you can write the statement is true for n is equal to 4, or P4 is true. Next. Next is inductive hypothesis. This is the second step. Inductive hypothesis. In this step, we suppose the statement is true for a positive integer k. Suppose that statement is true for n is equal to k, that is pk is true. Pk is true. In other words, you can write it as pk such that k factorial, by just replacing here n is equal to k factorial is greater than k square. This is our assumption when k is greater than or equal to 4. We say this is our inequality number 1. Next, we show that the statement is also true for n is equal to k plus 1. We show statement for n is equal to k plus 1 is true whenever pk is true, where the statement for n is equal to k plus 1 is given by, if we put here n is equal to k plus 1, we have k plus 1 factorial greater than k plus 1 square. To prove inequality number 2, we take the left side of this inequality, that is k plus 1 factorial, and we use the truth of inequality number 1, left hand side. Consider the left hand side of inequality number 2, k plus 1 factorial. If we break k plus 1 factorial, you can write it as k plus 1 into k factorial. Next, I am using inequality number 1. In inequality number 1, k factorial is bigger than k square. From 1, k factorial is greater than k square. So, if we multiply k plus 1 on both sides, this becomes k plus 1 factorial is greater than k plus 1 into k square. How can we obtain this step? Just by multiplying k plus 1 on both sides, this becomes k plus 1 into k factorial greater than k plus 1 into k square. So this expression k plus 1 into k factorial is bigger than k plus 1 into k square. So this. Next, I can obtain my inequality number 2, the right side of the inequality number 2, that is k plus 1 square. If I just replace here, k is equal to k square is equal to k plus 1, but with a logic. Next, as our k is greater than or equal to 4, as k square is greater than k plus 1 for all k greater than or equal to 4. You can check this. If you put here any k which is greater than or equal to 4, k square is always bigger than k plus 1. So if we put this k square here, this becomes k plus 1 factorial is greater than k plus 1 into k plus 1. That is, this is equal to k plus 1 whole square, and finally we can write it as k plus 1 factorial is greater than k plus 1 whole square for all a for all k greater than or equal to 4. Lastly, you will write as pk plus 1 is true whenever pk is true. Hence, by mathematical induction, we can say that Pn, the statement for n, positive integer n, is true for all n greater than or equal to 4. So this is a very easiest question. I hope you can solve the remaining part also. Next, we discuss the last question, that is question number 7. This question is also related to mathematical induction. Okay, let us discuss the last question of today's lecture. Question number 7. In question number 7, use the mathematical induction. We have to derive the following formula for all positive integer. The sum of the product of integer with its factorial is given by n plus 1 factorial minus 1. Let Pn be the given statement. You can write it as first we use the base step. Now our integer is starting from n, so we will write it here n is equal to 1. When you put n is equal to 1 here in the left side, for n is equal to 1, your statement is for n is equal to 1, we will take just the first term. If you put n is equal to 2, we will take the sum of two terms. So this is 1 into 1 factorial from the left side, and in the right side we put here n is equal to 1 in the formula. This becomes 1 plus 1 factorial minus 1. 1 factorial is 1, 1 into 1, this is 1. 1 plus 1, 2 factorial is 2. This is 2 minus 1, which is also equal to 1. So the left side is equal to right side. Hence the statement is true for n is equal to 1. Next, we suppose that the statement is true for n is equal to k. That is, we can write it as by putting n is equal to k in this formula. This become 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial up to so on k into k factorial is equal to k plus 1 factorial minus 1. Suppose this is my equation number 1. We show that the statement for n is equal to k plus 1 is true whenever pk is true. Where? What is the statement for n is equal to k plus 1? The statement for n is equal to k plus 1 is 1 into 1 factorial, 2 into 2 factorial up to so on. If we replace here n is equal to k plus 1, but we write the second last term, that is for n is equal to k. We have k into k factorial, and now I write the last term for n is equal to k plus 1. This is k plus 1 into k plus 1 factorial. This should be equal to k plus 2 whole factorial minus 1. The right side you can obtain just by putting n is equal to k plus 1 here. Now I will use the same strategy that I have used in the previous question. I will take the left side of this, and I will use equation number 1 here. So okay, the left hand side is this. I substitute these k terms, sum of k terms equal to this k plus 1 whole factorial minus 1. So the left side becomes k plus 1 factorial minus 1 plus the last k plus 1th term is k plus 1 into k plus 1 factorial. I need to show the right side k plus 2 factorial minus 1 by just taking common k plus 1 factorial from these terms, from these two terms. I have k plus 1 factorial. After taking common, here is 1 plus k plus 1 and this is minus 1. This is simply k plus 2 minus 1. Can you write this product as k plus 2 factorial? If you break this factorial, reverse, you can find this product. So this is equal to k plus 2 factorial minus 1, which is our required right hand side. Hence, lastly, you will write uh, the given statement for n is equal to k plus 1 is true whenever statement is true for n is equal to k. Hence, by mathematical induction, the statement is true for all positive integer. So, in today's lecture, we discussed from question number 5 to question number 7. In the next lecture, inshallah, we will start from question number 8. I hope today's lecture is beneficial for you. If you find my videos are helpful, kindly like, share. Inshallah, in the next lecture, see you again. Okay, take care. Allah Hafiz.